Hello, Math 141 enthusiasts. So here we are, the last section in Chapter 2, Section 2.8, the derivative as a function. And we're going to recap first what we talked about in Section 2.7. So in Section 2.7, we defined what f prime of a was equal to, and we defined it in really three different ways. First, f prime of a is the derivative of f of x when x is equal to a. From a rate of change perspective, f prime of a is the instantaneous rate of change of f when x is equal to a. And the graphical interpretation is that f prime of a is equal to the slope of the graph of f when x is equal to a. I'd like to spend a couple seconds on that. So if you remember in section 2.7, we defined f prime of a as the slope of the tangent line to the graph of f when x is equal to a. However, what we're really focusing in on is the slope of the graph itself. Now, that is very strange to think about because we usually don't think about finding the slope of a curve. We think about finding the slope of a line. However, since most of the quantities that we are going to be working with, if you graph what they look like, they're not going to be straight lines, they're going to be curves, and yet we want to find the quantity's instantaneous rate of change at specific locations. And since a rate of change is defined as a slope, it only makes sense to say that f prime of a, which is the instantaneous rate of change at a, is the same as the slope of the curve at a. So we use the slope of the tangent line at a to get us the slope of the curve at a. More of that will be coming in the future. So we saw two formulas for finding f prime of a. The first one, which is the original one, was f prime of a was equal to the limit as x approaches a of f of x minus f of a all over the quantity x minus a. Remembering that that fraction was the slope of the secant line through points P and Q, having coordinates a, f of a, and x, f of x. And we were looking at the slope of the secant line's behavior as x approached a, where x was the x coordinate of point Q and a was the x coordinate of point P. So that was the original version. The alternate version was f prime of a was equal to the limit as h approaches 0 of f of the quantity a plus h minus f of a all over h. In this particular version, instead of the coordinates of point Q being x and f of x, we redefined the coordinates of point Q using the horizontal distance between the x coordinates of P and Q. We called that horizontal distance h. So starting from A, going h, the x coordinate of Q was a plus h, and the y coordinate was f of the quantity a plus h. So instead of having x approach a, the limit is described, the slope of the secant line's behavior is described as what's happening to it as h, the distance, the horizontal distance between the x coordinates, is heading to 0. Now, the reason that we needed the alternate version is to get us to the formula for the derivative as a function. But before we get there, both formulas result in a number. F prime of a, what we saw in section 2.7, always turned out to be a number, represented the derivative of f at a, the instantaneous rate of change of f at a, the slope of the tangent line, and therefore the slope of the curve at a. But when we want to consider the derivative as a function, we need f prime of x. So that means we're expanding the notion of the derivative from a derivative at a point to the derivative of the entire function. And really, the only thing we have to do is in the second or the alternate version of the formula for f prime of a, we replace a with x. So instead of having a specific x value, we have a generic x value. So f prime of a, which equals the limit as h approaches 0 of f of the quantity a plus h minus f of a all over h, becomes f prime of x equals the limit as h approaches 0 of f of the quantity x plus h minus f of x all over h. So that's the only change that we make. Instead of having a specific x, we have a generic x. So for the limit definition of the derivative, which is right here, okay, this is what we call the limit definition of a derivative. And what it states is that the derivative of f is the function f prime of x is equal to the limit as h approaches 0 of f of the quantity x plus h minus f of x all over h. And this statement right here is important, provided the limit exists. What you have to remember is that the derivative at its core, at its root, okay, is a limit. And that limit has to exist in order for the derivative to exist. We're going to talk about what it means for a function to be differentiable and not differentiable. And it all revolves around whether or not this limit exists. So interpreting, okay, f prime of x is the derivative of f of x at any x, as long as the derivative is defined. F prime of x is the instantaneous rate of change of f at any x, and f prime of x is the slope of the graph of f at any value of x. Now remember, these are all contingent on f prime existing at the value of x in question. So here's an example. Now, what's going to happen most of the time when you're using the limit definition of the derivative, and the derivative is being defined as a function, when you evaluate the derivative, when you evaluate the limit to find f prime of x, you're going to get a formula. You're going to get an expression that contains x. Unlike in section 2.7, where we always got a number, f prime of x 99% of the time will result in an expression containing x. Sometimes, if the derivative turns out to be constant, then you're going to get a number, regardless of what x is equal to. But if you're not dealing with the derivative as being a constant, then you don't have to, that's not going to happen. You're going to get something that has an x in it. So what we can do, and here's an example to illustrate how it works. We have f of x is equal to 1 over x. Find f prime of x. So we know from the above definition that f prime of x is equal to the limit as h approaches 0 of f of the quantity x plus h minus f of x all over h. Now, unlike in section 2.7, we will not be filling in a number for x. We're going to leave it as x. Now, something you might remember from the previous section is that the two function notations in the numerator have to be replaced with their equivalent expressions. Now, f of x, well, that's just the function. That's 1 over x. Now, for f of the quantity x plus h, that's the value of function f when x is equal to x plus h. So remember how we evaluate functions, okay? Whatever is in the parentheses goes into all of the x spots in the formula. So since f of x is 1 over x, f of the quantity x plus h is 1 over the quantity x plus h. So we have f prime of x is equal to the limit as h approaches 0 of 1 over the quantity x plus h minus 1 over x all over h. So what we now have to do is we have to evaluate this limit, because the value of this limit, if one exists, is going to be what f prime of x is equal to. Now, as we've seen in most of the examples thus far, upon using direct substitution, we get 0 over 0, and that's no different here, because direct substitution, substituting 0 in for the h, we would get 1 over the quantity x plus 0 minus 1 over x all over 0. So the denominator is already 0. The numerator will be 0 as well, because you end up with 1 over x minus 1 over x. Recall that 0 over 0 doesn't mean that the limit doesn't exist. It means algebra is going to be necessary to get what you are taking the limit of into an equivalent version so that direct substitution can be used. Now, what we have here is a complex fraction, and if you remember from section 2.3, one of the limit techniques that we use, one of the techniques that we used to simplify the expression was to simplify the complex fraction. So again, how I simplify a complex fraction is I find the least common denominator of all the terms. In this case, that's x times the quantity x plus h, and I multiply each term of the complex fraction by that least common denominator. So 1 over x plus h gets multiplied by the least common denominator. 1 over x gets multiplied by the least common denominator. And the h in the denominator gets multiplied by the least common denominator. Now, in the numerator, we should have some things that cancel, and we do. In the first multiplication, the x plus h's will cancel, leaving us with 1 times x, which is x, minus. In the second multiplication problem, the x's will cancel, leaving us with x plus h. Notice the subtraction sign goes with that whole quantity, so I am putting the x plus h in parentheses. In the denominator, it's best not to multiply this out further. Leaving it in its quote factored form is going to make the simplification a lot easier. So in the numerator, if we distribute that negative, we get x minus h all over h times x plus h. The x's will cancel, become combined to a 0. So we have the limit as h approaches 0 of negative h over the quantity h times x plus h. Then the h that's in the numerator cancels with the h that's in the denominator. That's a common factor. So we have the limit as h approaches 0 of negative 1 over x times the quantity x plus h. And so now we use direct substitution. So f prime of x is equal to negative 1 over x times the quantity x plus 0. So f prime of x turns out to be negative 1 over x squared. So negative 1 over x squared is the derivative of f prime of x. What that means is that you can use this formula to find f prime of any value of x that you want, except for where f prime does not exist. In this situation, you couldn't find f prime of 0 because f prime of 0 would result in an undefined fraction. So if you wanted to find, say, f prime of 1, you can just plug 1 in for the x in this derivative formula. If you wanted to find f prime of negative 7, you could plug negative 7 into this derivative formula. So finding the derivative as a function opens up the possibilities of what we can do as far as the derivative goes. It's not that this supersedes what we did in section 2.7. It just makes what we did in section 2.7 a lot easier. All right. Now, as I mentioned before on the first page, the derivative only exists if the limit that it's defined as exists. So, when f prime of a exists, we say that f of x is differentiable when x is equal to a. Basically, differentiable means that you're able to compute the value of the derivative of the function at the specified value of x. Otherwise, if f prime of a does not exist, then f of x is not differentiable at x equals a. So going back to the previous example for the function 1 over x, that function is not differentiable when x is equal to 0, because f prime of 0 doesn't exist. If we plug 0 into the derivatives formula, we get an undefined fraction. So f prime of 0 doesn't exist, therefore f of x is not differentiable at 0. Now, we've now seen two different characteristics of a function's continuity and a function's differentiability. They mean two completely different things. All right, we saw in section 2.5 about the continuity of a function when x is equal to a. And that's where we were comparing the behaviors of a function at a, close to a, and were those two behaviors the same. So continuity at a was true if the limit as x approached a of f of x was equal to f of a. We just talked about differentiability at a. That means you can figure out what f prime of a is equal to. So really, f prime of a is another behavior of the function f. It describes f's instantaneous rate of change when x is equal to a. So continuity and differentiability are two completely different things. But there is an important connection between the two. Just as we saw there was a connection between average rate of change and instantaneous rate of change, there's a connection between differentiability and continuity. So this theorem, very important, it says if f is differentiable at a, then f is automatically continuous at a. So what this basically says is that if you know that f is differentiable at a, meaning f prime of a exists, it automatically 100% guarantees that f is continuous when x is equal to a. Okay? However, the reverse, which is called the converse, the reverse is not necessarily true. F being continuous does not guarantee differentiability. So what that means is that if a function is continuous at a certain x value, it does not have to be differentiable at that same x value. Differentiability automatically gives continuity, but continuity does not necessarily give differentiability. Now, is it possible for a function to be differentiable if you already know it's continuous? Yes, of course. Lots of functions at lots of different values of x fit that criteria, but it's not a guarantee. And so here are two situations in which a function is continuous at a, but not differentiable at a. Now, this sharp turn, okay, you can see that on a graph. So if a graph possesses a sharp turn of any type, meaning you could cut yourself on that turn because the turn is so sharp, that's what we call a sharp turn, and the function is not differentiable at the value of x where that sharp turn occurs. A common example, probably the best example to illustrate, is the absolute value function. Now, this is your standard absolute value function, which is the absolute value of x. And when you look at the graph, which is over here, the sharp turn occurs when x is equal to 0. And you can see that sharp turn as you move through the point when x is equal to 0. Now, when you take a look at the picture, it's pretty obvious that the function is continuous when x is equal to 0. There is no break in the graph of the function when x is equal to 0. And you could go through the continuity test to establish that the function's behavior close to 0 is the same number as the function's behavior at 0. But the question is, why isn't this function differentiable at 0? And again, it boils down to the fact that a limit will only exist, the derivative will only exist if the limit that it's defined as exists. So in this case, I'm going to be honest, using the f prime of x formula isn't the most prudent way to go about verifying, because we're talking about differentiability at a specific point. And so utilizing one of the formulas for f prime of a, which would be f prime of 0, is going to make this process a lot easier. The original version is the easier of the two. So I would say f prime of 0 is equal to the limit as x approaches 0 of f of x minus f of 0 all over x minus 0. Now what we know, of course, is that f of x is the absolute value of x, and f of 0 is the absolute value of 0, which is 0. So we end up getting the limit as x approaches 0 of the absolute value of x minus 0 over x minus 0, which gives us the limit as x approaches 0 of the absolute value of x over x. So this is the limit that we have to evaluate to determine if this function is differentiable at 0. There's just one small problem, okay? Some people, not you specifically, but some people may be inclined to say, oh, we can just cancel the x's, right? No, we can't cancel the x's because the numerator's x is an absolute value. The absolute value is not the same as parentheses, okay? So those x's cannot be canceled. So this is where the interesting part comes in. The absolute value of x is actually a piecewise defined function. The absolute value of x is defined as being x if x is greater than or equal to 0, and it's defined as being the opposite of x when x is less than 0. So depending on if you're on the right side of 0 or on the left side of 0, the absolute value function is defined differently. Now this brings into the picture that when a limit exists, the limit from the left has to equal the limit from the right. The limit that we're evaluating is a two-sided limit. Because that numerator is different depending on what side of 0 we're on, we have to consider the limit from the left and the limit from the right. So scrolling down to the next page, if we have the limit as x approaches 0 from the left. Now remember, from the left means smaller than the number in question. So when x is less than 0, the absolute value of x is equal to the opposite or the negative of x over x. Now we can simplify that. We get the limit as x goes to 0 from the left of -1. The limit of a constant is always the constant, so this limit equals -1. So from the left of 0, the function is headed toward -1. So coming in from the right of 0, means larger than 0. So when x is larger than 0, the absolute value of x is x. So we have the limit of x over x. That, of course, reduces to 1. And the limit of a constant is always the constant. So therefore, the limit as x approaches 0 from the right is equal to 1. Remember that in order for the limit as x approaches 0 to exist, what must be true is that the limit from the left of 0 must be equal to the limit from the right of 0. From the left of 0, the limit was -1. From the right of 0, it's 1. Last I checked, -1 was not equal to +1. So the two-sided limit does not exist because the limit from the left does not equal the limit from the right. Since the two-sided limit, which is what we were evaluating here, does not exist, and that limit represents f prime of 0, that means f prime of 0 does not exist, which means f of x equals the absolute value of x is not differentiable at x equals 0. Continuous? Yes. Differentiable? No. So we don't have the ability to find what f prime of 0 is equal to in this situation. And any variation of the absolute value function, you're going to have this sharp turn occurring. And the sharp turn graphically always occurs at the value of x that causes the absolute value quantity to equal 0. So the x value doesn't have to be 0. So it can, for example, if you have the absolute value of the quantity, x minus 3, let's say, this is equal to 0 when x is equal to 3. So this particular absolute value function has a sharp turn at 3, which means that function is not differentiable at 3. Continuous, yes. Differentiable, no. Okay. A second situation in which a function may be continuous but not differentiable is what we call the vertical tangent line. So basically, what we're saying here is that the tangent line to the curve exists at the point in question, but because it's vertical and the slope of a vertical line is undefined, and because, again, slope is the geometric interpretation of the derivative of the rate of change, having a vertical tangent line at a point means the derivative does not exist at that point. Okay, so good example to show this is that when f of x is equal to the cube root of x when x is equal to 0. So when we look at the graph, okay, there's the point when x is equal to 0. If we draw a tangent line at that point, oh, there is a tangent line. It's just vertical, which means that the derivative at that spot is not going to exist. So once again, why? Again, using the original version of the formula for f prime of a, we would have f prime of 0 is equal to the limit as x approaches 0 of f of x minus f of 0 all over x minus 0. So we know that f of x is the function, which is the cube root of x. F of 0 is 0. So we have the limit as x approaches 0 of the cube root of x minus 0 all over x minus 0, which gives the limit as x approaches 0 of the cube root of x over x. Now, this can be reduced, okay? Notice what we have here. We have the cube root of x, which is the same as x to the 1/3 in the numerator, over x in the denominator. We are dividing powers with the same base. When we're dividing powers with the same base, we keep the base, subtract the exponents, and the resulting exponent goes in the spot where the higher exponent was to begin with. So we have x to the 1/3 being divided by x to the 1st. Subtracting 1/3 minus 1, that of course is a negative 2/3, which is the same as 1 over x to the 2/3. So that's the limit that we have to evaluate in this situation. So this is a two-sided limit. Notice that if you attempt direct substitution, okay, we get 1 over 0 to the 2/3, which is 1 over 0. Raising to the 2/3 means taking the cube root of the number and then raising to the second power. Now, 1 over 0 is not 0 over 0. Okay, so 1 over 0 means that most likely the function in question, because there's a number not equal to 0 in the numerator and 0 in the denominator, that there's going to be a vertical asymptote when x is equal to 0. And so that means the limit itself is going to be infinite, meaning the function will increase or decrease without bound depending on the direction that you're coming from. In this case, what's interesting is that as we approach 0 from the left, that would be negative 0.1, negative 0.01, negative 0.001, and so forth. So what's going to happen in all of these cases, okay, and the calculator can help us out here, which is what the calculator is for, okay, if we take 1, okay, and we divide it by negative 0.1 raised to the 2/3 power, okay, that is going to give me approximately 4.64 as our function value. Then we would have 1 divided by negative 0.01 raised to the 2/3, which gives me 21.54 to 2 decimal places. And then we take 1 and divide it by negative 0.001. I'm actually doing this on the calculator as I'm talking. Raising that to the 2/3, and I did something wrong. You can't see my calculator screen, but I can. and I didn't get what I was looking for. And I still didn't get what I was looking for. I'm going to try this again. 1 divided by negative 0.001, and that's raised to the 2/3, not the 3/2, the 2/3. And looks like I'm getting 1, but that's bizarre. So 1 divided by, I'm going to try this one more time. Okay, so if I take negative 0.001, raise it to the 2/3, okay, I get 0.01, it looks like. I'm going to divide 1 by 0.01, and I divided by the wrong thing. This is what happens. That gets me 100. Notice what's happening is that those function values are increasing without bound. So approaching 0 from the left, the function 1 over x to the 2/3 is increasing without bound. Now, strangely enough, as we approach 0 from the right, we're actually going to get exactly the same values, because when we approached 0 from the left, we were dealing with a negative number. Taking the cube root of a negative resulted in a negative. Squaring a negative gives a positive. When you're dealing with positive numbers, taking the cube root of a positive gives positive, and then raising positive to the second power gives positive. So the function values are going to turn out to be exactly the same. So we have an increasing without bound situation, which means that this two-sided limit, because the function behaves the same on the left and on the right, we can say that the two-sided limit is equal to infinity, which means the limit does not exist because the function on both sides of 0 increases without bound. So this means that f prime of 0, which is what that limit represents, does not exist. So therefore, f of x equals the cube root of x is not differentiable at x is equal to 0. Now the behavior here is different, okay? What's happening is that as we approach 0, the derivative is becoming infinite, which leads to a vertical tangent line. That's different from the sharp turn that we saw with the absolute value. With the absolute value, we had a distinct limit from the left does not equal the limit from the right. In this case, the limit does not exist because the derivative's behavior is infinite in this situation. So, two scenarios in which a function is continuous but not differentiable: sharp turns in the graph of the function and vertical tangents associated with the graph of the function. Two more things before we wrap up this video and this chapter. There are some other notations for the derivative besides f prime of x. So when you see these other notations, dy dx, which is what we call Leibniz notation, it's named after Gottfried Wilhelm Leibniz, who was one of the two mathematicians responsible for developing calculus. The other, as you might expect, is Isaac Newton. They developed calculus simultaneously, but not together. And today's version of calculus is really a combination of the two. And dy dx is one of the contributions from Leibniz. Dy dx represents the derivative of y with respect to x. It means the exact same thing as f prime of x. If you have df dx, same thing, the derivative of f with respect to x. We have what's called ddx notation. So when you see d dx of f of x, that means the derivative of f of x with respect to x. We also have the capital D notation. Capital D of f of x means the derivative of f of x. You may also see a little x in subscript, okay? All of these symbols represent the same thing as f prime of x. So be on the lookout for these different notations. They all represent the same thing. Lastly, since f prime of x is a function in its own right, it may have its own derivative, which we would denote with 2 tick marks. That would be read as f double prime of x. Now, The number of tick marks that you see tells you how many derivatives away from the original function you are. So f double prime of x, because there's two tick marks, means you are two derivatives away from the original function. And we call that the second derivative of f. Now, another way of looking at f double prime is that it's the first derivative of f prime, because it's only one derivative away from f prime. The reason we're bringing up this notation now is because derivatives after the first one are what we call higher order derivatives. So that means you could have the original function, you could have the first derivative, you could have the second derivative, you could have the third derivative, you could have the fourth derivative. After 3 tick marks, writing 4 or more tick marks becomes cumbersome, so we switch over to normal looking numbers. So each tick mark represents how far from the original function you are derivative-wise, but each derivative can be interpreted as the first derivative of the function that it came from. As we move through the rest of the course, we're going to see uses for higher order derivatives, namely the second one, and we'll see that in chapter 4. So we have reached the end of section 2.8 and the end of chapter 2. Yay! So you've completed the first chapter that we have to take a look at. And so from here, we're going to be going onward to chapter 3. And what's in store in chapter 3? Well, you just have to wait until the next video. We'll see you then.